Hi everyone, I'm Mina. I'm going to talk about new techniques for providing fine-grained average case hardness. This is a joint work with Andrea Lincoln and Virginia Vassilevska Williams. So let's start with defining our goals here. So I want to understand how hard our favorite problems are on average, and we want to give explicit distributions over which we believe they are hard. So in fine-grained complexity, there are some problems that we call them core problems that people believe that they are hard. And if you want to prove hardness for a problem P, you reduce one of these core problems to your problem P. And you can see a list of these core problems on the left, some of them basically. So for average case hardness, we want to do something similar. We want to reduce a core problem in its worst case to the average case of our problem P. For this, in our paper, we use mostly three of these core problems: KOV or orthogonal vectors, zero KClick, and the KClick problem. And I'm now going to define these three. So let's first start with the KOV problem. So it says that given K lists L1 through LK of ND bit vectors for the in the order of polylog n, are there K vectors U1 through UK such that U1 of J to UK of J multiplies to 0, or in other words, these K vectors are orthogonal. So KOV hypothesis says that KOV requires n to the k minus the law of 1 time. And as a side note, we have that Seth or strong exponential time hypothesis gives us 2OV hypothesis. So next, let's define zero KClick problem. So it says that given a dense graph with large enough weighted edges, return true if there is a KClick whose edge weights sum to 0. And zero KClick hypothesis says that zero KClick requires n to the k minus the law of 1 time. And again, as a side note, APSP and K-sum have reduced to 0-3 click. Finally, the K-click problem says that given an unweighted graph, return true if it has a K-click as a subgraph and false otherwise. And the K-click hypothesis says that K-click problem requires n to the omega of K time. We have that ETH or exponential time hypothesis gives us K-click hypothesis. So this was a brief introduction of the core problems that we use, and I should mention that we mostly consider the counting version of them. So for example, counting K-click wants you to return the number of K-clicks in your graph. So now let's go back to the average case. Okay. So the first work that provided average case hardness was, with this approach basically, was Ball-et-al.'s paper. What they did was that for problem P, they found a polynomial piece of f sub P such that on an instance I, which is represented as a 0, 1 vector, f sub P on I equals P on I, or in other words, f correctly represents P. And they found this polynomial for a bunch of problems like counting OV or counting zero K-click with a constraint. And the constraint is that this polynomial should be a kind of low degree. So its degree should be n to the little o of 1. So why do they need this constraint? It's because of the next step. So far they've reduced P to computing f sub P, and now they have the self-reduction lemma that reduces computing f of P in the worst case to computing f of P in the average case. So let's see what this lemma is. So it says that let f be a degraded polynomial, let p be a prime number that is slightly bigger than the degree of the polynomial, so it is bigger than 12d, and let epsilon be a fixed number that is at most 1/3. Then if there is an algorithm that computes f with success probability 1 minus epsilon in time tn, where the input is taken uniformly at random from the prime field of order p. So this is the average case algorithm. Then there is a randomized algorithm that runs in order roughly tn times d time and computes f mod p on any instance with probability 2/3. So it gives us the worst case algorithm for computing f mod p. So it is essentially self-reduction for computing f mod p from the worst case to the average case. And if we want to basically compute f, the exact value of f, we can either consider a big prime or we can compute it for a bunch of prime numbers. This is how this lemma is basically used. So this is a key lemma that we're actually going to use a lot. Now let's have counting KClick as our core problem and also as our target problem. So I'm going to explain a step-by-step self-reduction for counting KClick problem from its worst case to its average case. We can represent counting KClick using a polynomial, which I'll show in a few slides. And so we get to the average case hardness of this polynomial. So we reduce worst case counting KClick to average case computing of f sub KClick. And this polynomial was first observed by Goldreich and Rothblum, and it was mentioned in Molotow's paper, and they use their self-reduction lemma to get to this average case. Then, if we want to go back to the original problem somehow, we can't just directly go back because these polynomials are more descriptive in general, and so they translate to a multi-edge version of KClick. So Goldreich and Rothblum stopped at this step and came up with a distribution on graphs for which counting KClick is hard on. Boat-Serra, Brannan, and Bressler reduced this multi-edge version to the regular version of KClick, so they basically got back to the average case counting KClick on Erdős-Rényi graphs. To see a high level, to see on very high level how this last step is achieved, let's see what the polynomial of KClick is. So it's easy to get it basically. So for each pair of vertices vi and vj, we have a variable e of vi and vj, which on an input graph G, it is 1 if the edge exists and 0 otherwise. Then we basically check for every k tuple we want through vk if they form a KClick by multiplying all variables associated to all the k choose 2 pair of vertices there. If this multiplication is 1, then they essentially form a KClick. And since we are summing over all sets of vertices, we count the number of KClicks. So this polynomial gives us the number of KClicks in the graph G. And it is also low degree. So its degree is k choose 2, and we treat k as constant, so the degree of this polynomial is constant. Now, in the self-reduction lemma, if you remember, the worst case to average case is over a finite field. So we end up at in the average case, we end up with numbers that are chosen from this prime field. So these numbers can be from 0 to p minus 1, where p is our prime number. And they basically can be as large as log n. So this is why we get back to a multi-edge version of KClick, because, for example, if E of Vi and Vj is 5, it means that we have 5 edges between Vi and Vj. So as I mentioned before, BBB gives a nice fix to this problem using a bit manipulation idea. So what they do is that they essentially produce many KClick counting instances from this multi-edge instance, such that in each instance, they only consider 1 bit of each of these variables, E of Vi and Vj, so that now they have a 0-1 input. But there are two things to consider here in order for this idea to work. So first, we need the graph to be k-partite, and it means that the nodes are the nodes should be partitioned into k parts that are independent sets. And second, these bits are not IID01 bits. In order for this to work, they have like a nice fix I'm not going to get into. But at the end, they get this nice result. They show that we can count K-clicks in worst case using an oracle that correctly counts K-clicks on a 1 minus 1 over polylog and fraction of Erdős-Rényi graphs. So this is step-by-step self-reduction for K-click counting contains a lot of ideas from different works. But these ideas are not actually bounded to K-click problem only, and we extend it to a general framework. So we define the notion of good low degree polynomials, or GDLP, and we say that a problem P has a good low degree polynomial f sub P if this polynomial essentially represents P correctly, meaning that on any input I, which is represented as an n-bit vector, f of I equals P of I, then we want this polynomial to be low degree. So we want its degree to be little o of log n over log n. And finally, we want it to be strongly d-partite. So it means that we want the set of variables to be divided into d sets, and we want each monomial to have exactly one variable from each set. So this is the definition of being d-partite for a polynomial. So why did we define this? Why did we define this notion? It is because of this theorem that basically says that problems with GDLPs have self-reductions from their worst case to their uniform average case. More formally, it says that suppose P has a GDLP, or good low degree polynomial. Suppose that there is an algorithm that takes as input an n-bit vector with IID 0, 1 bits taken from a Bernoulli distribution, such that it correctly solves P on 1 minus 1 over polylog and fraction of inputs and runs in Tn time. So essentially, suppose that we have this average case algorithm on uniform inputs with this success probability that runs in Tn time. Then there is a randomized algorithm that solves P on any input, so it's worst case, with probability 2/3, and that runs in order tilde of n plus Tn time. And order tilde neglects subpolynomial factors. To prove this theorem, we first reduce P to computing f sub P. And then we use the self-reduction lemma of Ball et al. To go from computing f sub P in the worst case to computing it on the average case. And then we use VBB's bit manipulation ideas to go to the uniform average case P. Now let's see what this framework gives us. So first, we show that counting any subgraph H in an Erdős-Rényi graph with success rate 1 minus 1 over polylog n is hard on average. And this was stated as an open problem in BBB, and they only proved it for counting K-clicks. Next, we try to basically try to see what problems have GDLPs, and we see that a lot of famous problems actually don't have GDLPs, like orthogonal vectors or 0-3 click, because whatever polynomial that we write for them, it is high degree. So because of this, what we do is that we define the notion of factored problems, and these problems together with our framework give us many results in average case hardness. So now I'm going to focus for a bit on these factored problems. Okay, so let's just start with factored OV. And then it'll become clear how basically the factored version of any problem is defined. So remember that in the OV problem, we're given n vectors, and we are asked if there are 2 vectors that are orthogonal. For example, here only V and W are orthogonal. Now, in factored OV, vectors are factored. So a factored vector consists of G sets of vectors of length B. And in this example, G is 2 and B is 3. So we have each factored vector consists of 2 sets of vectors of length B, of length 3. And the intuition is that a factored vector represents all vectors that can be formed by choosing one vector from each set, basically. So, for example, if we represent the vectors that U represents with S of U, then S of u equals these 4 vectors that you see here. And S of v has 6 vectors, and S of w has no vectors because the first set of w is empty. So this is the definition of factored vectors. Now let's define factored OV. So factored OV asks, are there factored vectors u and v such that there are vectors x in S of u and y in S of v such that x and y are orthogonal? Note that x and y are now just normal vectors, so orthogonality is defined for them. Now counting factored OV, says that for each factored pair of vectors u and v, count the number of orthogonal pairs x and y where x is in S of u and y is in S of v, and then sum all these numbers for all the factored vector pairs. So for example, in our factored OV example, we have 8 orthogonal vectors. So the answer to the counting factored OV problem here is 8, and W has no vectors, so all these orthogonal pairs come from S of U and S of V, and like as an example, one of the pairs are shown in red here. Okay. Let's define factored problems in general. So factored problems are defined on problems that are k-partite. So it means that the set of the input vectors is divided into k parts, and we are looking for k vectors, exactly one taken from each part, such that they satisfy a property. For example, in KOV, they should the property that they satisfy is that they should be orthogonal, and in the counting version, we basically want the number of these the number of k tuples of vectors that satisfy the property. Now, in factored P, instead of vectors, we have sets of vectors because we have factored vectors. And then the factored P says the following. So it says that choose one factored vector from each part and one vector from each factored vector such that these k vectors satisfy the property that P asks for. And this is exactly what we did for factored OV, factored KOV. As we said before, a factored vector consists of G sets of vectors of length B. And these two numbers, G and B, cannot be just anything. They have these two bounds. So B should be little o of log n, and G should be little o of log n over log n. And this is because we want to have this theorem that says that factored problems have good low degree polynomials. So this is essentially why we defined factored problems, because we wanted a class of problems that have GDLPs. So let's first see how the world of factored problems are and basically what relationships they have. So I'm going to represent a problem P that is k-partite with KP. And as I mentioned, for these problems, we can define their factored version. And we have that KP reduces to factored KP. So any problem reduces to its factored version. And it kind of says that the factored version of any problem is kind of harder than the original version. Then we show that we can reduce factor KP to factor K XOR. And then a factor K XOR, factor K sum, and factor KOV, they reduce to each other. They are complete for the class of factored problems. And then factor K sum reduces to factor 0 KClick. So the reason that I've divided this figure in two parts is because factored 0 KClick doesn't have only vectors as inputs. It also has a graph as an input. So it kind of shows that we can define factored problems on for problems that are not they don't have only vectors as their input. And so the problems that are on the right-hand side, they only have vectors as input there. And another thing to note is that the running time that we use for these reductions is n to the k minus log of 1. And this means that some of these factored problems are much harder than their original versions. Because, for example, we can solve k-sum in n to the k over 2, but factored k-sum is conjectured to be hard. It's like it can not have an algorithm that runs faster than n to the k minus log 1. Okay, let's see what results we can get from these factored problems. So we said that factor kp has a good low degree polynomial, and we had this theorem that if a problem has a good low degree polynomial, it has a self-reduction. So we have worst case to average case reductions for factored kp and a uniform average case reduction, basically. So factored problems are one class of problems for which we have average case hardness, and they are not the only class. So we reduce some of these factored problems to other problems that are not factored. I have regular expressions as an example here. So the regular expression problem is the following. It takes as input a regular expression p of size m and a sequence of symbols, or we call text, a t of length n, and asks if there is a substring of t that can be derived from p. And we show that over a sequence of reductions, we can show average case hardness for counting regular expressions from Seth, or strong exponential time hypothesis, where we use factored 2OV as our middle step. And the distribution over which counting regular expression is hard on is not uniform, but it is a natural and easy to sample distribution. So all our results are of this flavor, mostly. So we start from some core problem, and its worst case, we reduce it to some factored problem. Then we use our theorem, our self-reduction theorem, and we get to the average case to this factored problem, and then we reduce this factored problem to our problem P, to our target problem P, and so we get an average case hardness for our problem P. So here, this is the map of our results. It has a lot of problems, but the thing to note is that there are some core problems that I've shown in green. They're on the right. So we start from them. We have some factored problems that are shown in orange. They are in the middle. And then we finally get to some non-factored problems, just some regular problems that are shown in white. And we get average case hardness for them. And you can see like KLCS and edit distance among them. And the distribution that these problems are hard on average, it's not necessarily uniform distribution, but it's again a natural and easy to sample distribution. Okay, so to show you, basically there are many directions for fine-grained average case complexity, and to just show you the potential of this field, from BBB's paper in last year's Fox to today, there has been 3 independent works building on it. One was our paper, one was the recent Soda paper of Hirahara and Shimizu that showed results for average case complexity of biclick under Seth. And the third was Goldreich's paper that gave a nice proof for counting KClick's mod 2. And you can see that over the course of 1 year, there has been 3 independent works. So it shows kind of that there's a lot of directions and potentials for fine-grained average case complexity that hasn't really been explored yet. Thank you for listening to my talk.